All right, in this problem, they tell you the electric field in a region is pointed away from the z-axis. So there's the z-axis, and the magnitude depends on the distance s from the axis. The magnitude of the electric field is given by a constant divided by s, where alpha is a constant. So this far away, the magnitude, it's pointed away from the z-axis, and the further you go, the smaller the field gets, the magnitude. Okay. You can produce, you've seen this before, you can produce a field like this if you have a uniformly charged infinite line charge, and the electric field is given by 2k lambda, the linear charge density, divided by r, where r is this distance. Okay. And in this problem, r is called s. Okay. So they're using s for the distance from the axis of rotation. So that's what produces a field like this. And what they want you to find is, find the potential difference between points P1 and P2. P1 and P2. So they want you to find V2 minus V1, and it is given by this line integral, E ds from 1 to 2. Okay, so to do this line integral, you have to choose a path in going from here to here to do that line integral. So how do we choose the path? Why don't they give you the path? It doesn't matter. This value of this line integral is independent of the path. That is for fields, the electric fields that are created by static charges. Okay? Such fields are conservative fields, and the line integral is independent of the path. Okay? Now, this problem has cylindrical symmetry, so you want to use cylindrical polar coordinates. Okay? And for cylindrical polar coordinates, for these set of coordinates, ds, or well, I'll use dr is ds s hat, okay, plus s d theta theta hat plus dz z hat. Okay. So what this means is the following. So in Cartesian coordinates, dr was equal to dxi plus dyj plus dzk. Okay, what was this? What did this mean? This is an infinitesimal displacement, and this displacement consists of, you go along the x-axis, dx distance along the x-axis, follow that by dy distance along the y-axis, and then dz along the k-axis. Okay, so for instance, okay, so you go dx along the x-axis, dy along the y-axis, and then dz along the z-axis, and this was equal to dr. Okay, so that was the definition. So for this guy, I'll draw. So for cylindrical symmetry, okay, again, we'll use the Cartesian coordinate as reference, x, y, z. But if you have cylindrical symmetry, you draw circles. This would be, so here we are using s as the radial distance. S hat is that vector. Theta hat is this vector. And then z is the vector pointing in the z direction. So this is theta hat, and this is z hat. Okay, so now dr and small distance is ds s hat. So you go a little distance parallel to s. This is ds plus anyway, you'll learn all of this in Calc 3, I believe, if you haven't seen it already. S d theta, and then this is so this is s d theta, and then so this ds would be s d theta. That small distance is s d theta, and it's along the theta hat axis. And then any distance you go in the z direction, dz z hat. All right, what this is showing you is it's breaking down an infinitesimal displacement along the three mutually perpendicular directions, okay? We do this for problems that have cylindrical symmetry, and you use this when you use Cartesian coordinates, okay? Like I said, you speak the language that is convenient for the corresponding problem, for the problem that you're solving, okay? So for our case, for cylindrical symmetry, we're going to use this, okay? And also, since the line integral, this value of the line integral is independent of the path taken from going from here to there, there are an infinite number of paths, okay? We'll choose the path where calculating the line integral is the easiest. And that path happens to be this. And you'll see in a second. Okay, so we'll go from P1 to P2 along this circle and then along the radial direction. Okay, so I'm going to call this path 1 and then path 2. Okay. All right, again, what is it that we're trying to calculate? We're trying to calculate the electric potential difference between this point and that point. What is the voltage between this point and that point? That's what we're going to calculate, okay? Now, if this alpha is positive, then this point will be at lower potential than that point, okay? And if alpha is negative, then this point will be at higher potential than that. But again, that's an aside. Okay, so let's do this. So, okay, in here we've used ds, so I'll write that as ds, that infinitesimal distance as d. Okay, so, all right, so we'll substitute that here. And the electric field is given by the electric field vector. Here's and s hat, it points radially outwards. At every point, it's pointing radially outward. And so there's the formula for the electric field. Now, if you take the dot product of these two guys, E dot ds, okay, only S dot S will survive. S hat dot theta hat is 0, S hat dot Z hat is 0. Okay, those are mutually perpendicular. So the only thing that survives is alpha S ds. Okay, and that's the reason why we chose cylindrical coordinates to do that line integral. Okay. All right, so V2 minus V1 equal to minus E dot ds, and we'll go path 1 plus path 2. Okay, so path 1 was this path, and path 2 is this path. I guess. All right, so the line integral is minus. You can see when you're going along this path, the only thing that's changing is theta. You're traveling along theta hat, and along this path, E dot ds is 0. So along path 1, this line integral is 0. Okay. And so this is equal to minus E dot ds along path 2. Okay. Now along this path, ds is only equal to that. So E dot ds is just this, okay? And S changes from A to B. Okay, so this along path 2, this is equal to and it changes from A to B. All right, so this is minus alpha ln S A to B. So let's actually rename this again. So in fact, VB to VA equal to minus alpha log B to A. Okay, so what we are saying is these lines are equipotential surfaces. Potential at radius B minus potential at radius A is given by this expression. So potential at radius at distance B from the z-axis minus potential at distance A from the z-axis is given by that formula. Okay, so cylindrical surfaces are equipotential surfaces. Yeah. Okay, in nuclear fission, a nucleus splits roughly in half. Okay, so you take a neutron, and some of you went on the field trip and saw this nuclear reactor. Right, so in a nuclear fission reaction, you split this into two nuclei. Okay. And once they split, they have potential energy. Okay, so they're both positively charged particles, and so it's like a compressed spring, and they fly apart. These guys will fly apart. Well, where does that energy come from? Okay, so what has happened is when you split these nuclei, by the way, so you get 3 more neutrons. When you split these guys, the energy is coming from these guys are more tightly bound. Okay, so the mass lost is what is converted to energy. Okay, and again, like I've said, like we've said before, you burn 1 carbon atom, and the amount of energy you get is about 4 eV. You split this nuclei, you get about 200 MeV. Okay, 50 million times more the energy per atom. Okay, and that's the lure of nuclear energy. And in addition, there's no carbon dioxide emission, okay, which is a greenhouse gas. So per molecule, per atom, you're getting 50 million times more energy. Okay, so in nuclear fission, a nucleus splits roughly in half. What is the potential? What is the potential energy from a fragment? Oh, what is the potential that distance from a fragment that has 46 protons in it? So what they're asking you is what is the potential at this distance from one of the fragments? What is the potential energy of a similarly charged fragment at this distance? And then finding the potential energy of these two guys. Okay. Potential from a point charge is kq by r, electric potential. Okay. The charge is 46e divided by r. Okay, so k is 9 times 10 to the 9. That is the Coulomb's constant. 46, and the charge of a proton is 10 minus 19 Coulomb, and you are 10 to the minus 14 meters of it. So the electric potential right next to one of the fission fragments is this. Okay, and so this is 10 minus 10, and then you get 10 to the 4. So equal to 9 times 46 times 1.6 divided by 2 into 10 to the 4 volts. Okay, that's the unit. So right next to one of the fission fragments, the potential is 3 million volts, 3.3 million volts. Okay. The potential energy between the two fragments is K Q1 Q2 divided by R. We've already calculated this guy, which is this value. So we'll just multiply that to Q2 by Q2. So the potential, QV, Q is 46E and V is 3.31 into 10 to the 6 volts. And this is 10 to the minus 13. And what are the units for this? I'm sorry? No, this is energy, this is in joules. We haven't converted it to MeV yet. All right, so this is the potential energy in joules. Okay. Now, they want you to calculate what is the potential energy in MeV, okay, in million electron volts. So there is a different energy of unit of energy, which so different fields use different units. That's their preferred unit. Why do we use different units?
methods work easier in different circumstances.
Yeah, and what is the reason for that? See, even though you're walking around with a supercomputer, you can remember only small numbers. See, you don't give distances to Orlando as 1,344 meters. Okay, you gave it as 60 miles. You chose the unit of miles because then that distance can be small. You never tell your age in seconds, do you? Okay. So, all right. So when you want to calculate the energies of these guys, if you calculate, see this number, who will remember this number? Okay. So this is the potential energy between two fragments. You can't remember those numbers. So what we'll do is we'll calculate it in MeV, and then you'll get small numbers. All right. So by the way, so here's the conversion. 1 electron volt is 1.6 into 10 minus 19 joules. So 1 MeV is a million electron volts, is 1.6 times 10 to the minus 13 joules. Okay, and so this becomes, so U is 243.6 into 10 minus 13 joules times 1 MeV. This conveniently cancels. Okay, so this number you can remember, 150 MeV. Yeah. So like I said, the energy released in this process is about 200 MeV. This guy has about 150 MeV, and the other 50 MeV is over there. Yeah. And then in a nuclear reactor, your goal is to use one of these guys to create a further reaction. If you want a bomb, then you have to have more than one of them create a further reaction. And if you want to kill the reaction, then you want less than one to make a further reaction, and eventually it'll die. So in a nuclear reactor, you maintain criticality, and maintaining criticality means getting one of these guys to produce a further reaction. Okay. In a particular region, the electric potential is given by this formula. What is the electric field in this region? So you saw that electric fields, how are they related to the electric potential?
It's the negative gradient.
Negative gradient, very good. Yeah. Okay. So that's how electric fields and potentials are related. Del V by del X. Okay, so you're differentiating this with respect to X and keeping other variables constant. So this will give you minus y squared z plus 4y. Del V by del Y, this gives you 2y, and that'll give you 4x. So that gives you minus 2xyz plus 4xj. And this del v by del z, this gives you minus xy squared, and this gives you 0. So minus xy squared. All right, so if you want, you can, so y squared z minus 4y I plus 2xyz minus 4xj. Okay, so there's your electric field. Yeah, so this is how electric fields and electric potentials are related. And when is this true? For what kind of fields is this true? Huh? Very good. And the other name is conservative electric fields. Yep. We will introduce an electric field produced by changing magnetic fields in a couple of 3 chapters. Then that electric field won't be related. It's not related like that. That'll be a non-conservative electric field. I guess. So that's coming 3 chapters from now. Yep.
So whenever you differentiated, you did only the variable that was given, like at the beginning?
Yep.
Like the x to the d, okay, I see.
Yep. So what this means is, how is v changing when you're moving parallel to the x-axis? What this means is, how is v changing when you're moving parallel to the y-axis? Okay.
Okay.
And this means, how is v changing when you're moving parallel to the z-axis? This gives you the surface charge density on a long straight metallic pipe is sigma. What is the electric potential outside and inside the pipe? Okay, so assume the pipe has a diameter of 2a. Okay, so when they say it's a pipe, I guess this is hollow. But if you put any charge, the charge resides on the outside, on the outer surface, and this is infinitely long. You've seen this before. The electric field outside is 2k lambda by r, where r is the distance measured from the center. The electric field inside is 0. Okay. The electric field, for instance, inside a metal basketball, if you put a charge on the outside, is 0. Okay. All right. Now we have to find lambda in terms of sigma. Sigma, they give you the charge density per unit area. What is lambda? Lambda is the charge per unit length of the cylinder. Okay. So A is the area, A is the radius of the, okay. So sigma is 2 pi A times unit length times 1 times, lambda, what's that? So lambda is 2 pi A sigma. Okay, so they want you to calculate the electric potential outside and inside. So what we'll do is we'll do the line integral from A to R. Okay, VR minus VA equal to minus E dot ds from A to R. Okay, again, the line integral is independent of the path, so we will use cylindrical polar coordinates, and we'll go straight out like that. Okay. So VR minus VA equal to minus 2k lambda r hat, and ds is I'm going to and the only term that will survive is dr. So only r hat will survive. Okay, so the line integral is minus 2k lambda r dr. Okay, again, I don't want to write primes, so it just gets messy. This is an integration variable, and that limit, I'm using the same notation. So VR minus VA, and the value of this, the integral is log R. Okay. So this is the value of the integral at R. Okay, if you put R equal to A, this will be 0. Okay, and that's fine. This would be 1. Log of 1 is 0. So that expression is correct. Okay. So this is the potential this is for R greater than A. Okay, so at R equal to A, this term is 0, so you can define whatever constant you want to define. Okay, so if you hooked up a 10-volt battery, you can call that 10 volts on VA. Okay. Okay, what about at inside points? So now what we'll do is we'll do an integral from A to B. Okay. So now we'll do an integral from A to B. And here's B inside point. Okay. Except that everywhere inside the electric field is 0, so this line integral is 0. So VB is equal to VA. So everywhere inside the potential is the same as the potential on the surface. Okay. So again, I'll give you another example. What this means is if you take a basketball, a metal basketball, put charges on it, okay, and charge it to, let's say, 1,000 volts, okay. The potential everywhere is 1,000 volt, and inside the basketball, the electric field is 0, and it's 1,000 volts everywhere, okay. And outside the basketball, this is acting like a point charge, and the electric potential is falling off as 1 over R. Okay. So for instance, if the radius of the basketball is 5 centimeters, at a distance of another 5 centimeters from the basketball, or at a distance of 10 centimeters, the potential would be 500 volts. Okay, it would be, R would double and, okay, it would be. Okay. So this problem says, find the electrostatic potential energy of 8 equal charges, 3 microcoulombs each, at the corners of a cube of side 2 centimeters. So the charges are sitting on the corners. All right, the potential energy is the potential energy of all the independent pairs. This pair, this pair, these pairs. Okay. The side is this side is A, which is 2 centimeters. This diagonal, oops. Okay, this diagonal is root 2 by A. And that diagonal is what? Yeah, A square plus A square, that would be root 2 by A plus A square, root 3 by A. Okay, so that diagonal is root 3 by A. All right, the potential energy is all the independent pairs. The potential energy for one pair, okay, all the charges are equal. Okay. So, how many of these do you have? 1, 2, 3, 4 of these guys, and you have 6 faces. Okay. So 4 times 6, 24. Oh, actually, okay. So this pair, oops. We'll take this pair, each pair gets counted twice. It's getting counted on this face and it's getting counted on that face. Do you guys understand? So it's 24 divided by 2k q square by A. The distance between the pairs is A. All right. Okay, so let me go over that again. We're calculating the potential energy of all the pairs. For this pair, this pair, this pair, and this pair, that's 4 per phase, 4 per phase. And then there are 6 phases, so there's 24 of those, except that each pair is getting counted on this face and the bottom face. It's getting counted on 2 faces, so that's why I divided that by 2. Okay, now we'll calculate these parallel faces, these guys. The distance between them is root 2 by times A. There's 2 per face, and nothing is getting counted twice. Okay, so that's 6 times 2. Plus 6 times 2 k q square by root 2A. Yeah. And then how many of these guys do you have? 1, 2, 3, 4. 4 of those guys. Okay. Okay, so k q square by A is common. 12 plus 12 over root 2 plus 4 over root 3. Yep.
counting each point 3 times instead of 2? Because you have,
Mm-hmm.
each point is a vertex of 3 sides.
Mm-hmm.
And if we're counting 4 points per side, then we would hit the same point 3 times, right?
Okay,
For the first section.
for this guy?
Yeah.
Uh, For this term, are you talking about this
Yes,
term?
that one.
Okay, so this term is potential energy between this guy, this pair, this pair, that pair, and that pair. That's 4 pairs, 4 identical pairs.
Okay.
That's the potential energy of a single pair times 4,
Yes.
okay? And then you have 6 faces to the cube, so there is the 6. But this pair got counted on this face and that face. That guy got counted twice. So that's why I had to divide that by 2.
It's the pairs.
Yeah,
That
yeah.
makes sense.
For these pairs, there's no mixing. So there's 2 per face, and then 6 faces. For these diagonals, there's only 4 of those. 1, 2, 3, 4. So that's the potential energy of this cube, of this constellation of charges. Okay, so actually this could be the potential energy of a constellation of galaxies. All you have to do is replace K by G and Q by the masses. Okay, all right. So